Well, welcome to the penultimate lecture on transition metal chemistry. It'll be this one, which will be relatively short, and one more. And for the topic for today, what I want to address is one of those stranger things, if you will, in organometallic chemistry. And that is that ligands can bind to a metal not through their sigma electrons, but through their pi electron cloud. And we'll look at a few different examples of ligands that can do this. So, the classic one, and the one that revolutionized this entire field, in fact, is called cyclopentadienyl. Cyclo for cyclic, penta 5-dienyl, a diene, and the ul ending, YL, means anion. So if you start with this thing, this is cyclopentadiene. And what you can do relatively easily is use a relatively strong base, and one of these would actually be, for example, the organolithium reagents that we were talking about earlier in the class. And so we could specify that. N-butyl lithium. What this will do is it'll abstract one of those protons. And so what will happen then is we'll lose butane. That doesn't really matter. And this anion has now taken away one of the two protons. And so, if you're still in practice of assigning formal charges to donor atoms and things like that, if you have a carbon with 3 bonds, so we do 1, 2, and 3, and 2 lone electrons, which we now have, that carbon is negatively charged. And so we call that cyclopentadienyl. So this is an extremely important ligand in organometallic chemistry. Now, one of the things you might note, if you remember back to organic class, or even if you've not had that, and maybe you haven't seen this before, but we have 2, 4, 6 pi electrons, right? And whenever that happens, and you have a delocalized pi system, what you get is an aromatic compound. And so, you'll normally see this representing that. This is also cyclopentadienyl. And it is aromatic, which means all the electrons are delocalized. That's why we draw a circle in the middle of it, like we would for another molecule. That's aromatic, and that's benzene, and we'll get to that in a minute. But remember this. We have 6 pi electrons. That's going to come into play when we try to figure out how many coordination sites does this thing take up. So, as mentioned, right, this is a historically significant ligand because where it was first found out to be was in the compound ferrocene. And so if we go back to our formula, and let me redraw it. This way, okay, each one of these points represents a carbon. And if you saturate the rest of the carbons, each one of them has one hydrogen on it. So another way you might write this formula is C5H5 minus. And yet another shorthand abbreviation for this, which we won't use for very much of this stuff, is CP minus, cyclopentadienyl shorthand, reminding us that we have a minus charge on there. So, when ferrocene was first prepared, this was in the 50s. And unlike now, where you can get the exact structure of a molecule using X-ray crystallography relatively quickly, this wasn't possible. So, the people that synthesized this molecule thought it looked like this. And the way that they made it was by taking a lithium salt of cyclopentadienide and adding that to iron 2 chloride. And you get 2 lithium chlorides as a byproduct. So this is what they thought the structure was. This is at my house, by the way. If you hear the phone ring in the background, that's the roofer trying to tell me that I need to have my roof fixed because of the large hailstorm we had 2 weeks ago. So, sorry about that. Anyway, you can tell just from this, hopefully, that if we have 2 negatively charged ligands, that this is iron 2, it's D6. But as the coordination number 2, which is what this suggests. And obviously, by the way I said that, if you're used to the way I talk by now, the answer is no. So, there were 2 individual teams that discovered that molecule simultaneously, one in the United States and one in the United Kingdom. And in the United Kingdom, they had a really good X-ray crystallographer at the beginning of that field by the name of Sir Geoffrey Wilkinson. And if you take advanced organic chemistry or something like that, you'll get really familiar with that name. He was able to do an X-ray crystal structure of the molecule. And we won't go into what all of that entails, but basically what it allows you to do is to get an exact picture of a single molecule by shooting X-rays at it and see how they bounce off the electron cloud. And it turns out that that structure that was up there is actually not correct at all. It's this one. We have one of our cyclopentadienyl rings. We have the second. And in between is the iron. And so this is what's called, again, a real clever name here, a sandwich compound. There's the bread, there's the cheese, or the ham, or whatever you're eating in the middle. It's an iron sandwich between 2 planar, and they are planar. So if you look at this side on, it basically looks like this. Those rings are completely flat, so if you looked at it on the edge, they would look like they were planes attached to the iron. Now, how does this happen? And what's going on here? Well, are all 5 of the carbons bound to the metal? Yes, but not in the way that we've been talking about before. Because remember, to form a metal ligand bond, what you have to do is you have to be able to attach the ligand to the metal using electrons. And to attach 5 atoms through sigma bonds, like we've been doing, would require 10 electrons. We don't have that many. We have only 6. And so, these are coordinated to the iron through the pi electron cloud of the ferrocene. That's why they sit like this and aren't sigma attached like the first structure we had up there before. And so it's the pi electron cloud of the ligand that attaches to the metal. Okay, so this is, again, a little bit odd, but we already ascertained that this is iron 2. And if you look at your periodic table, you start with 8, you lose 2, you get 6. It's a D6 configuration, which is very common for iron. And you can also represent this like this. C5H5 in parentheses 2 Fe, or even CP2Fe. And you'll see these used interchangeably all over the place if you start looking up this molecule, for example. So the last question then is, what's the coordination number of our iron? And so we have 5 carbons in the top ring, we have 5 carbons in the bottom ring, that's 10 carbons total. Is the coordination number 10? No. And that's again the difference when you start having ligands that bind to metals through their pi electron cloud. And so in this case, then there's a very specific thing that happens. And that's the following. And so this is the big takeaway from what we're talking about here. We have 5 carbon atoms, but we've already said you're not going to take up 5 coordination sites with one of these ligands. And the other thing we said that I told you to remember, we have 6 pi electrons. Okay, so that being the case then, how do we figure this out? Here's how you figure it out. Each pair, not each individual, each pair of pi electrons takes up 1 coordination space or 1 coordination site. So if things are sigma bonded like we've done with everything else before, it's how many things are attached to the metal that gives you the coordination number. Here, we're doing something a little bit different. And it's this part of the statement that's important. So how many pairs of pi electrons do we have? We have 6 pi electrons total. Six pi electron pairs. That means that each one of these things is going to occupy 3 sites. or spaces. You can use either one. So then if we go back to the formula, or you can draw the structure either way. Each one of these takes 3 sites. We've got 2 of them. The coordination number is 6. Ferrocene is 6 coordinate. So we said this is a really common coordination number, and there it is again. And so we won't go into every single kind of ligand that can do this, but there is one other one that's common and kind of important. And it's a little different than this one, because remember, and you do have to remember this one, C5H5 is C5H5 minus. Cyclopentadienyl is a -1 charge. But there's another ligand that does this very commonly. C6H6. If you draw the formula of that, I'll just remind you that there's 6 hydrogens around the periphery. This is benzene. You'll also see this represented because, again, it's an aromatic system with 6 pi electrons. You might see this, and you will see it, drawn like that. This and that are equivalent. But the difference between this guy and this one is benzene by itself is not charged. It's neutral. And so cyclopentadienyl -1, benzene, neutral molecule. And this can make sandwich compounds too. And here's again a classic example going back to maybe the 1960s with some historical significance. That. Bisbenzene chromium. So once again, our rings are planar. We have 2 rings right on top of one another with a metal in the middle. It's a sandwich compound. Now, the thing about this is, what's the charge on the metal? How many d electrons does it have? And what's the coordination number? The answer to that is, all right, we start with chromium. We can write the formula like that. These ligands are neutral. They have no charge. Therefore, the chromium has no charge either. Right? You don't have any charge over here that you have to balance over there like we've been doing. So benzene being a neutral ligand is like, say, having an ammonia or something like that. Right? The ammonia is neutral. So the benzene is neutral too, so chromium is neutral. Therefore, chromium 0. Look at where this metal comes in the periodic table. It's in group 6. It hasn't lost any d electrons because it is not charged. And finally, what's the metal coordination number? Well, going back again to the more elaborate structure of benzene, we have 246 pi electrons. That breaks down to 3 pairs. Therefore, the coordination number of this is also 6. And so you can have other ligands that do this. There's a few examples on the handout that comes with this virtual lecture 12's handout. And this is how you go about figuring that out. But the thing is, you don't have to have 2 of the same ligand in these things either. So let's look at an example where we do not. Inevitably, of course, what is this going to be called? Well, it's the 3-legged piano stool. There's the seat, there's the legs. Okay. But now we've got a mixed ligand system here. And how do we go about figuring out all this stuff, these 3 things? Charge, d-electron count, coordination number. Well, the first thing you've got to be able to do is figure out what the ligands here are. So let's start with our now hopefully familiar ligand CO. This is the structure of the bonds anyway. I put the formal charges on. This is the one probably time you'll see it where there's a positive charge in the oxygen. And we'll get into it a little bit more in this one in the next lecture. But we have a negative charge and a positive charge. So no charge overall. All right. The halogens should be by now really simple for you to do. We remove the halogen in its nearest inert gas configuration, which means this chlorine already has 6 lone electrons around it. They're seldom ever shown in a formula of a compound like this. But these bonding electrons come with when you take the ligand off, and therefore we have 7 electrons to start with, no bonds, and 8 lone electrons, -1. And then finally, this is why you have to remember it, that this is not only C5H5, it's C5H5 -1. So what we have is manganese 2. If you look at its position in the periodic table, you'll find it at the top of group 7. If you lose 2 d electrons, you start with 7. You go to 5. What's the coordination number? Again, this takes 3 sites. Then we have 1, 2, 3. Coordination number of 6. And so, basically to make this really short and simple, if you can remember that this is negatively charged, and it takes up 3 spaces, you don't have to go through the exercise of figuring it out every single time. So, That's how these ligands can bind to their pi electrons. But let's look at one more thing. And I'll just mention this now in case you end up in the 4000 level inorganic class. The rings can slide around. And so in every picture that we've had, they're symmetric with respect to the metal, which means the metal is directly below the middle of the ring. They can skew to one side or the other, and then not all 6 pi electrons are binding. Sometimes it's only 4, sometimes it's only 2. We won't get into that, don't worry about that now, but you may see that in the future. But let's look at the situation where you have 2 electrons binding to a metal. And so let's take a simple example. An alkene, and R is whatever you want. So you could have methyl groups on the ends, you could have ethyls, you could have some really gigantic thing, it doesn't really matter. These can bind to their pi electron cloud too. And so we can come up with many examples of this. But these can bind like so, and let's say we've got a 5-coordinate, I just gave it away, a 5-coordinate chromium complex. What's the charge on the chromium? What's the d electron count? We already know the charge. Going around and around and around. Those are neutral. This is cyanide, very common ligand, negative charge. What about this? When an alkene binds through a pi electron cloud, remember, that was a neutral molecule. Nothing has changed. We haven't taken off an R group and attached it, through one of these carbons or anything like that. And so this ligand is also neutral. So now I've got chromium 2+. That's D4. Coordination number is 5. So when an alkene binds like this, it takes up one site. And this is consistent with what we said before. There's one pair of pi electrons in there. The other part of the double bond is a sigma bond, so it doesn't get involved. One pair of pi electrons. One site. And finally, for this lecture, alkynes can do this too. So what if they do? Again, let's take do a non-symmetric one, why not? That's an alkyne. It's again neutral. And it can bind to metals through its pi electron system as well. And so, trying to think of a different metal to use here. How about this one? A vanadium complex. Or let's make, let me redraw. Let's make our alkyne at the back. And so this is straightforward. Those are all -1 charge. They're halogens. This one, because it's binding through its pi electron cloud, is an alkyne, is neutral. But how many sites does it take up? And this is where there can be a little bit of confusion. But when you do this, it's only one of the 2 pairs of pi electrons that bind to the metal. The other one that's there, whichever one you want, the left-hand one or the right-hand one, doesn't get involved. And so it takes 1 site. Consequently, the coordination number of this complex is 6, and we have vanadium 5+, which is D0. And so these are the only, essentially, 4 examples of this we need to worry about at this level. Cyclopentadienyl, how it binds, remember, -1 charge. The benzene molecule, how it binds, neutral. Alkenes and alkynes, both neutral, both only take up 1 site, despite the fact that there's 2 pairs of pi electrons there. And so that's all really we need to worry about for this. This will pertain to homework number 6 and doing some more of this d-electron counting and all that stuff. And there'll be one more lecture to follow, lucky number 13. So I'll see you then.